Hello, welcome to lesson 1-6, scientific notation. We use scientific notation for very large numbers. For example, measurements that we would take in space, or measurements that we might take in biology when measuring the size of a cell, or when measuring the size of an atom. Let's look at this real-world link. Electronics. A single-sided, single-layer DVD has a storage capacity of 4.7 gigabytes. 1 gigabyte is equal to 10 to the 9th power bytes. Write a multiplication expression that represents how many bytes can be stored on a DVD. Well, it's telling us that there are 4.7 gigabytes, and that each one of those gigabytes is the same as 10 to the 9th power. It's equal to 10 to the 9th power. So really, we could say that 4.7 times 10 to the 9th power would represent the number of bytes on a DVD, right? Because they're saying that that's how much space there is, and each one has this much. So we just multiply it. This is essentially what we call scientific notation, when we are able to represent a number in the units value, right? Or the first value is in the ones, and then we would multiply it by the number to the 10th power to represent how big it really is. For example, 4 times 10 to the first power. Remember, we don't have to write to the first power. We can just say 4.7 times 10 moves the decimal place over 1 to the right side to make the number bigger, and it makes it 47. 4.7 times 10 to the power of 2 is the same thing as saying 100. You see that? And it's going to move the decimal now over two places to make it 470. Right? We can continue that pattern, and now we see that it's to the 3rd power, so it's going to move the decimal place over 3 times to 4700, 4,700. And again, continuing with that pattern, now it's going to move it 4 places to the right. So if it's 4.7, and it's going to move it 4, because it's 10 to the 4 power, right, it's going to go 1, 2, 3, 4, right? So another 0 there, another 0 there, another 0 there, and it becomes 47,000. So we just moved the decimal to the right, correct? We just went to the right each time, to the right like that. And that's because we have a positive exponent. But what if we have a negative exponent? Look over here. We have 4.7 times 10 to the power of negative 1. Now that you've seen in the previous lesson negative exponents, you know that the decimal is now going to move rather to the right. It's going to move to the left, right? So it's going to go this way because we're multiplying it by a fraction. Whenever you multiply a number by a fraction, it becomes the fraction of that number. So if we're multiplying 4.7 times 1/10, this value is going to move to the 1/10. You see? So it becomes 4,700. If we multiply it by 100, this value here will move to the 100th. So the decimal has to move over 2 times. So now it becomes 0.047. 4.7 right here times 10 to the negative 3rd power. It's going to move over 3 times now, right? 3 times to the left. Make the number even smaller. So one more time here, really. So it went from here, 1, 2 for this one, and one more time will be the 3rd one. So it would be 0.0047. So it's 47 10,000ths. And then finally, it's going to move 4 times. So it'll be 0.00047. And you can see now that we're working with very small numbers. This is a tiny number, right? So that's why we would use scientific notation to express very small numbers or very large numbers, as you see here. Number 3. If 4.7 is multiplied by a positive power of 10, what relationship exists between the decimal point's new position and the exponent? When the power is positive, the number of exponent gives the number of places the decimal point moves to the right in the product in the answer. What we mean is that this right here, the number of the exponent gives the number of places the decimal point will move to the right. So here it's telling us it's going to move 2 times to the right. So it looks like this. You see that? Because it was just there. So it was here before, and then it goes 1, 2. Oh, I put too many zeros, sorry. So it would be 470. Moves 2 places to the right. Number 4. When 4.7 is multiplied by a negative power of 10, how does the new position of the decimal point relate to the negative exponent? It's essentially the same, but instead of moving to the right, it's going to move to the left. So when the power is negative, the number of the exponent gives the number of places the decimal point moves to the left in the product. Same as I mentioned before. Let's say 4.7 times 10 to the power of negative 2. It's going to tell us how many times it's going to move to the left. So it would be, it's going to move 2 times. It's going to be 0.047. It went from being here, 1, 2. So for a key concept, you can go ahead and make a note of this. Scientific notation. Scientific notation is when a number is written as the product of a factor and an integer power of 10. The factor must be greater than or equal to 1 and less than 10. So meaning the number has to be in the ones place. Okay? So for example, do you see this number here? It's in the ones place. So it has to be a number between 1 and 10. And you should be able to multiply by a power of 10. 10 to the 8th power. So that this is going to tell us how many times the decimal is going to jump. And if it's going to jump from the 4, right? We started here at the 4. Let me zoom in. Right there, we're going to count 8 spots. Ready? 1, 2, 3, 4, 5, 6, 7, 8. There you have it. So this is written in scientific notation. So by now you've seen me do a couple of examples, and here's a couple more that you can take a look at. One with a positive exponent and one with a negative exponent. And you can see how many times the number moves. It's to the power of 4. So it's going to go from here, 1, 2, 3, 4. And here it's to the power of negative 3, so it's going to go to the left, 1, 2, 3. Okay, you can pause and analyze these a little bit more if you need to. Or you can go right ahead now and jump to A, B, C. Try A on your own and then watch how I do it. Pause now. Okay, so we have 7.42 times 10 to the 5th power. It's going to move my decimal over 5 times. So I'm going to make spaces 1, 2, 3, 4, 5. Each space here I have to add a 0 to it. Okay, so it becomes 74,000, oh no, 742,000, right? Yep, 742,000. Let's try B. Okay, now we have a negative exponent, which means it's going to move how many places to the left? 1, 2, right? So it would look like this. I could do here 1, 2. So it's going to look more like 0.061. Okay, and let's try C. going to move it 2 times, right, to the right. It's a positive exponent, so 1, 2. It's going to look more like 371.4. Okay, I hope that's making sense to you. Now, we can go the other way. Now you can be given an extremely large number as 3,725,000, and you're being asked now to write each number in scientific notation. You're going the other way. This is what we're looking for. Okay, here's 2 examples of a very large number and a very small number. Go ahead, pause the video, take a look through them. And if you're ready, try these 3, D, E, and F, and then you can check my answer. Pause now. I hope you paused the video. Okay, remember, our decimal needs to end right in here, right? So that the numbers is between 1 and 10. And it's over here now. So let's see. It's going to have to jump to go from here to here. Is going to be 1, 2, 3, 4, 5, 6, 7. It's 7, so it's 10 to the power of 7, right? And we can write it as 1.414 times 10 to the power of 7. Okay, if that's confusing to you, remember that the numbers, it's very large. It's a very large number, and we're trying to make it as a number between 1 and 10. So we have to put the decimal place right there to make a units, the ones. And then when we multiply it, it's going to become this large number. So it has to be a positive exponent. Here we have a very small number. And again, the decimal's right here, and it needs to go right there. This time the decimal is going left. 1, 2, 3. Going to -3, right? So we can now multiply 8.76. And F, again, we have a small number, okay, and we want to put the number in the ones. So remember, we want the decimal to be there. If the decimal is going to be there, when we actually write it up as the real number, it's going to have to go left. And it's going left by 1, so it's going to be to the -1. To the base of 10 times 1.14. Feels like I'm writing it backwards, but I'm able to do it correctly like that because I count the number of places that it's going to move after we find the product of this, right? So I do that so that I'm able to identify what my exponent will be. Then I write it to the base of 10, and I write it as a decimal where I wanted the decimal to be. I realize this lesson has a lot of examples. We're already on example 5, and we're just barely getting into the word problems. Refer to the table at the right. Order the countries according to the amount of money visitors spent in the United States from greatest to least. So people from these countries visited the United States, from Canada, India, Mexico, and United Kingdom. And they spent money, dollars spent. So visitors from Canada spent this much, visitors from India this much, Mexico this much, and United Kingdom that much. So what they want us to do is put them in order. Now, clearly, you can see that Mexico spent, actually no, you can see that Mexico has a bigger number right here, right, in the ones. But when you actually look at the exponent, it's going to tell you how many times the decimal is going to jump, and this one's jumping by 1 more place value. So this number much bigger than this number. But you can see that United Kingdom has the 1. They both have the same exponent, but when you go over 2 place values, they have a 6 here, and we only have a 3 in Canada. So the United Kingdom is definitely the biggest number. Then Canada, then Mexico, then India. If you were not able to figure it out like that, please go ahead, pause the video, and look at them again. It is also being explained here. As you can see, they're telling us how to compare Canada to the United Kingdom. And we're going to compare these two because they both have the same exponent, the same power of 10. Well, these two also have the same power of 10, but we're just comparing the number between 1 and 10. Here we have another example so that we can practice. Some of the top U.S. cities visited by overseas travelers are shown in the table. Order the cities according to the number of visitors from least to greatest. So these are the famous cities in the United States, and these are the numbers of visitors they saw. Let's find the largest number simply by looking at the exponents. So the two biggest numbers are right here in the middle, okay? Vegas and Los Angeles, right? Because they're both to the power of 6, right? 10 to the power of 6. And then, now that we know that these two have the same number of place values, we compare the number. And 2 is greater than 1.3. So it would be Los Angeles would be first. Actually, a lot faster if I just write LA. LA is greater than Vegas, right? Now let's look at the ones that have power of 5. We see that we have they both of those do, but Metro DC area is larger than Boston, which is at 7. So it goes DC is greater than Boston. Now let's pay attention to the question. The question is saying order the cities according to the number of visitors from least to greatest. So from least would be Boston first, then DC, Metro DC area, then Vegas, and the biggest one is LA because they want us to do least to greatest, so we're reading it backwards. Number 6, there's a STEM challenge with the answer. If you could walk at a rate of 2 meters per second, it would take you 1.92 times 10 to the 8th power seconds to walk to the moon. That's a huge number. It is more appropriate to report this time as 1.92 times 10 to the 8th power seconds, or 6.09 years. Explain your reasoning. What would be more logical? If it took you this long to walk to the moon or this long to walk to the moon? Well, the measure 6.09 years is more appropriate, right? Because we want to talk about time. How long will it take you to get there? The number 1.92 times 10 to the power seconds is very large, so choosing a larger unit of measure is more meaningful. We don't want to measure how many seconds it'll take to get to the moon. We want to measure how many years, because we know how far it really is. Right? Seconds, I don't even really know how many seconds are in a year. So it would be better to just measure by the year. So now let's analyze a question very similar together. In an ocean, the seafloor moved 475 kilometers over 65 million years. Almost 500 kilometers the seafloor has moved in 65 million years. Is it more appropriate to report this rate as 7.31 times 10 to the negative 5 power kilometer per year, or 7.31 centimeter per year? Explain your reasoning. Well, I think you can agree with me when we say that it's a lot easier to imagine what 7.3 centimeters are per year, because we know how much a year is because we've lived more than a year, right? We have birthdays every year, and we can pick up a ruler and easily see how many 7.3 centimeters are. But it's really hard for us to imagine millions of years. So using this number is really tough for us to measure. So in other words, I would use 7.3 centimeters per year. It is more meaningful to use smaller numbers. And here's your private practice. Remember to preview the practice. Make sure you feel comfortable doing this so that you are ready for class. See you then, everyone.